Okay, thank you. And I want to thank the organizers for the possibility to give this talk here. So my title is Isometric Approximation in Bounded Sets and some applications. In the abstract I mentioned that I will start with approximation, but then I thought that it's better to start with the applications so that I don't have to worry about the timetable so carefully in the end. And everything that I present here in our work is joint work with Dimitri from Novosibirsk and also some parts with Jussi Väisälä from Helsinki. So I start with some mappings. The main or the most important mapping for this talk is this last one, but let's first think about some other condition. So we have a near isometry, epsilon near isometry, a mapping which changes distances only in some additive way, and usually the additive constant epsilon is rather small, but of course in the definition it can be anything. Some people like to write the condition in this way, but somehow I prefer this one, and I mention both of them so that nobody can say after this talk that I didn't understand anything. They are equivalent. And the second condition, the bi-Lipschitz condition, need not be 1 plus epsilon bi-Lipschitz, but this will be the case during the whole of this talk. And these two conditions are closely related because this condition implies the near isometric condition. If I continue from there, and we have a bounded set then you get the near isometric condition for 1 plus bi-Lipschitz map with a constant epsilon plus the diameter, and the same way in the other direction. Additive error term is much easier to handle than this multiplicative bi-Lipschitz constant, so this near isometry will be a very useful tool later on. So our main goal is to extend mappings. Yesterday there was a nice introduction to Whitney type extension problems, but here we start with injections. So the mapping is injection in some subset A of Rn, and we want to extend it to homeomorphism to the whole space. And we want to do this in some quantitative way, but of course it's not so clear what we mean by this quantitative way. And there are some obvious problems that can arise, so it's easy to map a round circle to some knot where the extension doesn't exist for topological reasons, even if the mapping is Lipschitz or bi-Lipschitz with some reasonable constant less than 10. Or there may be homeomorphic extensions, but the quantitative part goes well. So if you ask somebody in the street, is this curve a nice curve, they will say that it's very nice, but mathematicians can do something strange for these curves. So if you map a heart into a kidney, you know what happens if you go to a hospital and this happens, you change kidney and heart and it's very bad. So this mapping is also bi-Lipschitz with a reasonable constant, but it doesn't have extension to the whole plane as a bi-Lipschitz map, because these cusps where the angle should be 0, you can't turn this outward cusp inside with a bi-Lipschitz map in the plane. Of course you can do it in 3 dimensions, but that's a different thing. So we need some real restrictions for these mappings so that we can do this. There are some positive results, for example by Tukia and Väisälä and Blackfullin and other people, but I don't think I have time to go there now. So this is one of our main results. We have a set in Rn. There's some strange condition. It should be sturdy with some constant c. And then the result is that for small epsilon, all 1 plus epsilon bi-Lipschitz maps can be extended to the whole space. And the main point in our constructions is that this error term is optimal in some sense. It grows linearly in this epsilon, not some square root of epsilon, but only c times epsilon. I will explain this sturdiness a little bit later because I don't want to now go into some technical details in the very beginning. But let me just say that, for example, if you have a nice domain with smooth boundary in any dimension, it will satisfy this condition. Or if you have z to the power n in Rn, it will satisfy this condition. Or if you have the snowflake curve in the plane, it will satisfy this condition, and so on. So it's rather general geometric condition, but it doesn't require any manifold structure or anything. So the set can be like an open set, or it can be very discrete, or some strange combination of all these things. And because the converse is true in 2 dimensions, so if all 1 plus epsilon bi-Lipschitz maps from this set A can be extended in this way to the whole plane, then the set must be sturdy. So it means that this is the right definition, at least in the plane, for this problem. Okay, so this is for bi-Lipschitz maps, and then I want to present similar results for quasi-symmetric maps. So we need some definition. It looks a little bit strange if you have not seen it before, but I think one easy way to think about it is that we have x, and then we have some points z and y in some sphere around x, and we look how the map F maps these points. So because the distance from z to x is the same as y to x, it follows that, for example, if y is something that minimizes this distance to the boundary and z is something that maximizes the distance, then you see that this ratio L divided by L cannot be bigger than this eta function at point 1. And the eta is some strictly increasing function, just strictly increasing.
Sorry, what is the graph eta? Or what the
Eta, the same function as in the definition. So this is the typical graph of eta t. It's 0 and 0 and then continuous, strictly increasing. So it controls the way in which ratios of distances are changed. And of course, if you have a bi-Lipschitz map, then you can choose eta t with a very easy calculation. It's the Lipschitz constant squared times t. But in general, these mappings need not be by Lipschitz. They are more closely related to quasi-conformal mappings. And if you have a mapping of the whole Rn, then it's exactly the same as quasi-conformal. But this can be defined without any derivatives or anything like that for arbitrary metric space. And the trivial cases are those where the eta function behaves in a linear way. So it measures how far is f from a similarity. Similarity preserves all the ratios of distances. And so in general, this function that controls this quasi-symmetric map can be any homeomorphism of the positive real axis, but in practice you have to think very hard to find examples where you can't use this kind of easy power type formula. So the power type formula behaves like this. It's first like square root and then x to the squared, something like that, and with some constant c. Relatively connected contains all connected sets. It contains all self-similar Cantor sets, so it can be really disconnected, but in some controlled way. I have the definition at the end, but I will never get to that, and I don't want to spend time for that, because this is only for motivation for our real definition, because we want to consider these maps so that they are very close to a real similarity. And this general theorem says that this power type is very natural, so we make all the constants in the power type definition close to 1, and then we get the definition that we need. Well, 1 minus epsilon is not the same as 1 over 1 plus epsilon, but don't worry about that. And so this is the extension results for this kind of maps. We have again this geometric property, sturdiness for the set where the original map is defined, and then we show that for small epsilon these epsilon power quasi-symmetric maps can always be extended to the whole space Rn, and again in the best possible way the constant cannot behave better than c times epsilon. Again, there will be no square root of epsilon or anything, so it's optimal in this sense. So let's think about how to prove this kind of results. Maybe I draw a picture of the general idea. So this is our set A, where the original mapping is defined, and we want to define the function outside so that it will extend this original. So we use the rather usual Whitney type extension. We take a Whitney cube and maybe some triangulation, and we want to define the extension in the vertices of the Whitney cube. So what we do, we take the closest point in A, then make some rather large ball which contains not all of A, but some reasonable part of A, which is the radius of the ball is comparable to this distance. we approximate the original mapping F in this intersection, A intersection, there is B, 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 R, and because the original mapping is, let's say, close to almost like, well, 1 plus epsilon bi-Lipschitz, for example, we can approximate it very well with an isometry. And then we use the approximating isometry to define the value of the extension at this point. But this must be done very carefully, because if we take another vertex of the Whitney cube, then maybe the nearest part of A may be now here, and the extension will be defined using some approximating isometry in this area, which may be rather far from the other part. And the only way we can control that these don't overlap, and the result will be a homeomorphism after some affine extension, is that we must be able to control the different isometries in this part and this part and somehow everywhere. So this is how we come to these approximation results, and let me start with this classical result. It's called Hayes-Ulam theorem in very general setting for Banach spaces. And now we have this epsilon near isometry, a mapping which moves points, changes distances with an additive constant epsilon only. And the result is that there is a real isometry from the whole space. It will be an affine isometry, surjective, so that the approximation is very good, and especially it's linear in epsilon. And here's some history about this constant C. The first proof was with C equal to 10 and only for Hilbert spaces, and it took 60 years to find a 2-page proof with the best constant C equal to 2. And there were very many intermediate results. But this is for mappings defined in the whole space, so it's not interesting for us because we want to extend mappings, and the extension is very easy if the mapping is already defined in the whole space. So we need to go into subsets and try to find approximation results for subsets. And the first case is we take the unit ball, and then it turns out that if we have epsilon near isometry in the unit ball, then we can have logarithmic dependence on the dimension, but then again linear in epsilon. Then if we go still into more general case, the set is only contained in the unit ball and contains orthogonal vectors. Then we get linear bound in n, and again linear in epsilon. And it seems my other clock is stopped, so maybe I have infinite amount of time. But the other clock says that there are still a couple of minutes. I think I'll skip this example so that I can define the concepts that are needed in our theorem. So thickness is some geometric concept for a set. We try to squeeze it between parallel hyperplanes and make the distance of the hyperplanes as small as possible, and then this infimum will be the thickness. So this looks awful, but if you look at the picture, it's much easier to understand. But for thickness, you don't need any measure. You need just a couple of points which show that it cannot be squeezed very small between between hyperplanes. And then this is the main result that we need for this extension. In thick sets we can approximate near isometries with real isometries. And again, so that we have some constants but linear dependence on this epsilon near isometry. Constant epsilon. So let's end with this definition of sturdiness. So the main idea is that we need thickness for this set, not globally, but in all intersections. A intersected with every ball should have reasonable thickness, something related with the radius. But so this is called uniformly thick sets satisfy this for all balls. But if we want to have a general extension problem, then we should also allow some separate isolated points, because if we have function defined in isolated point, everybody can extend it to a neighborhood very easily. And so the sturdiness condition will allow this isolated point case. It will be no problem for extension, and it's included in the definition. So I think I must stop here. Thank you for your interest.
Please, questions or comments?
There is well-known notion of bodies of constant width. Is there something similar for bodies of constant thickness?
I haven't thought about it because it's not important for this extension, but of course it's a natural question, so maybe it need not be a set ball into that constant width, because even in the plane it's not necessary.
I think it would be interesting for people to see if the set is not sturdy, not thick, then there is no linear approximation, but it is square root approximation.
Yes, yeah.
If you
it was in the. So without this thickness, this is the best we can get in the approximation. So the easy example is if you have a straight line, it's not thick, and you can just map it a little bit higher, and it may seem strange, but this doesn't have this extension property, so that the error is constant times epsilon, but it will be constant times square root of epsilon. And this is not thick, it's very thin.